I think we can start now. It's
Yeah. Yes.
Okay, so let's start this second lecture of this series by Professor Solomon Friedberg from Boston College. And the title of his talk is From Harish-Chandra to the Langlands Program, an Introduction. So welcome, Professor Friedberg.
Thank you. Thank you very much, Manish, and thanks to everyone for coming. It's a tremendous pleasure to be here to speak in this program. I wanted to start by saying that I've had the pleasure of visiting Pune before, and together with Raghuram, I actually was organizing a conference there in BC before COVID. And so here's a picture with, in fact, a bust of Harish-Chandra, and behind that is a document describing in brief some of his contributions. So it's really very meaningful to be here and to be connecting again with my many friends in Pune and throughout India and throughout the world who are interested in this topic. I'd like to start with some discussing a few works of Harish-Chandra very briefly, but showing you them, and then make a bridge to the Langlands program. And I know there was already a talk 2 days ago doing that, so my talk in some ways will be a bit different in style. It'll be a little bit less rich in terms of details, which I think Minyoung gave a lot of, but then I hope trying to give a bit of an overview of what comes of this circle of ideas that might be of interest. It might help frame some of the future lectures, and I even will mention a couple of the talks that are going to come in the course of my talk. So I'd like to begin by this wonderful volume of Harish-Chandra. Here it is, and then I scanned it at home a couple of nights ago from 1968, his Springer lecture notes, Automorphic Forms on Semisimple Lie Groups. And it's exciting to read and to look at, even all these years later. And so here's a page from the book. He gently credits Mars for taking the notes and says that he hasn't personally checked all the proofs. And then begins with an introduction. The error here is in my scanning. I didn't hold it down long enough, so I apologize. But you can see let G be a connected semisimple Lie group with finite center, and then he looks at a space of L2 functions on G that are gamma invariant. I'll be putting gamma on the other side, but of course it's the same space. And then, just to remind you of where we were all those years ago, this volume says go to page 3 because our friends at Springer did their best, but somehow the pages didn't end up in the correct order, so you have to do a little bit of looking. But of course, the content is what's important, and it's beautiful content. This work is complemented by a paper that Harish-Chandra wrote in Proceedings of the National Academy of Sciences from 1959. And I actually thought I would start by just looking at the review of that paper, because I think it's a good lead-in to this lecture. So G, a nice Lie group, connected semi-simple with a finite center, K, a maximal compact subgroup. And then he's going to talk about a space of automorphic forms. And he's going to look at functions that transform under gamma by means of a character, which he calls mu, under the compact subgroup K, a maximal compact subgroup, by means of a finite, of course, finite dimensional, so irreducible representation, sigma. And then as well, I'm looking at functions that are eigenfunctions with respect to the center of a universal enveloping algebra. And of course, as the seminar has talked about, Harish-Chandra did tremendously pioneering work on understanding representations of real Lie groups. And so this was a natural condition. Such a function's analytic. And he studies the space of such functions with a growth property. And the main theorem is that this dimension is a finite dimension. And so this is a space of automorphic forms of a particular type, and it's a finite dimension. And this really started, I think, this was fundamental to the whole subject. And then one can study the action of the regular representation on this space, and this decomposition on L2 induced by the action of G. Each discrete irreducible component occurs only a finite number of times. And so this is a fundamental understanding of a space of functions which satisfy this analytic condition, this different set of differential equations number 2, and also have this invariance property with respect to gamma, a discrete subgroup. And to launch the talk, I just wanted to point out that a couple of remarks are useful. So Harish-Chandra showed that this dimension of this space, sigma u chi, is finite. And so then, of course, maybe we could ask the question, what is it? And that turns out to be a hard question and is not understood in even the simplest cases. So when I was a student, I learned so much mathematics that was all put together, and I always appreciated very much seeing things that weren't known. So I wanted to maybe point out that here right away, we immediately come out with questions that are still to this day not understood. We could take G to be the simplest case, SL2R, say K to be SO2R. Take the trivial representation, I think of, oh yeah, sorry, gamma. Let's of course choose gamma to be the obvious thing, gamma SL2Z. And then there's supposed to be a representation of K and a representation of gamma, and we'll choose those both to be trivial. And then we're, because G mod K can be identified with the complex upper half plane, we end up looking at functions on the complex upper half plane that are eigenfunctions of the Laplacian. I don't think Harish-Chandra called it lambda, but since it's an eigenvalue, I'll call it lambda. And I'll be and as we know, lambda is far greater than a quarter. I mean, Selberg conjectures for congruent subgroups that that's also true. Still not known. But then we could ask, what is the dimension of this space? And we expect that the answer is always 1. And these are things that Langlands would label in the part of the L2 space that is transcendental. More about that coming in a couple of minutes. And there's sort of no good reason why we should expect this space to be more than one-dimensional in this situation. But even now, we don't really know if that's true. We expect that that dimension is always 1. And you could also ask the same question, changing Z and the underlying field Q to another number field. And here we can do numerical experiments. So I have a student who's actually found the first example of an analog of this, a Bianchi-Moss form, where the underlying ring of integers is not Euclidean. He's found it numerically, and indeed it does seem to be one-dimensional based on the numerical experiments, but we don't have a really good reason for knowing that. We don't know that that's true. And in fact, if you ask this question for more general groups, it turns out to be a very subtle question. We might want to take this space F0 and decompose it into pieces. We might look for a finer decomposition, and that brings up lots of ideas that Langlands brought to the fore about things like L packets. And even there, it's really a subtle question, and it gets into, say, work of Blasius for SLN, where n is greater than 2, and understanding the dimension of the space. Gan and Zhang, and understanding, say, a similar question for G2 and showing that very surprising things happen. But we don't really understand this dimension. And I guess that's my point. Harish-Chandra proved it's finite, but we don't really understand it. Secondly, I wanted to, though I'll be introducing this part of, the ideas of the Langlands program, I did want to think about some of the future talks in this series. And instead of L2 of what Harish-Chandra was writing, G mod gamma, I'll put the gamma on the other side of it later, we might look at L2 of X, where X is a G space, some kind of, say, a manifold, an orbifold or something. I mean, an algebraic variety that has a G action on it. And that brings up what will eventually get called the relative Langlands program. So I'll introduce the standard Langlands program now, but we can imagine more general spaces of functions, and making sense of what L2 of X even means is maybe not so apparent. And so much later in this series, Spencer Leslie, my colleague at Boston College, will be speaking about the relative Langlands program, which brings up ideas of Saklarides and Venkatesh and Ben Zvi, for example. And one more comment before jumping into today's lecture in more detail. We're going to look at the space of functions and think of it as something where the group acts, and so it's realizing a piece of a representation, and we'll be thinking representation theoretically. But I wanted to point out that the functions in F0 of G mu chi, to use the notation that I showed you from Harish-Chandra's paper, the functions in F naught G mu chi are important as functions, not just as, say, generators for a representation space. And what I mean by that is functions have things like classes of Fourier coefficients. And so much later in this series, Daniel Persson will speak, I think he's not scheduled until August, about connections to non-perturbative string theory. And what's sort of striking in the work that he'll talk about is that it's the functions that matter and less some of the machinery involving L functions that I'll be describing in a few minutes today. But just the space of functions, which again, I think Harish-Chandra really helped us understand, plays all sorts of roles in different ways. And it's important. It has questions about it. It can be generalized. And the functions in this space are very important functions. So this series really builds on Harish-Chandra's work in many different ways. And the circle of ideas has gone in many different and I think very exciting directions. Okay, so I wanted to now, after those remarks, talk a little bit about the Langlands program. And I'd like to start on with an arithmetic situation, and I won't give you the most general situation, but let me just take, say, K over Q, a Galois extension, and imagine that we have a representation of the Galois group of Q into aught V. So where V is a finite dimensional complex vector space. Okay, then quite a long time ago, Artin defined an L function attached to this information I'll call it LS rho. And it was defined as a product over the primes where there's a finite number of primes where we need to make adjustments. And what Artin proposed to do is to take a characteristic polynomial. So we'll take the identity on V, that's an n by n identity matrix. And
so do you mean F should be QK, right? I think.
Oh, I'm sorry.
F is F equal to K or something? Yeah.
I'm sorry.
F, yeah, that's it. Yeah.
That was my I think that was a K, but it looked like an F, so I apologize. Good. Okay. So so what we might need to do to make an Euler product is we might want to find some things in the Galois group of K over Q. And what we get is not quite an element, but rather a conjugacy class, the Frobenius of P. So this is a conjugacy class. And that at least works if P is unramified. And so then there has to be some further discussion if P is ramified. And so we'll take that, will give us some, if you will, an n by n matrix, an invertible n by n matrix. So we'll take the characteristic polynomial evaluated at P to the minus S inverse. And again, there's some adjustment if P is not unramified, I have to restrict to the stabilizer of the inertias group. So here, almost all factors are of degree n in e to the minus s, but then a finite number might be smaller. And so this is the thing that Artin proposed studying. And maybe as a first example, I might just imagine that the dimension of V is 1 and rho is trivial. And then what we would recover is simply the product over all P of 1 minus P to the minus S inverse. And that, of course, is the Riemann zeta function. Okay, so this is somehow a broad generalization of the Riemann zeta function. And Artin proposed that something special happens. I mean, the Riemann zeta function, as we know, has analytic continuation and a pole at S equals 1. But Artin conjectured that is really the only case that we get a pole. That so if rho is irreducible, say, and non-trivial, then in fact LS rho continues to an entire function. Okay, so we can make sense of it for all complex S and its entire. And I mean, in fact, Artin's example, Artin proved this, say, when K over Q is abelian. And in that case, the proof shows that LS rho is equal to, so it's identified with an L function coming in a different way, LS chi, where chi is a Dirichlet character. And Dirichlet characters, of course, have been understood. Dirichlet studied primes and arithmetic progressions and introduced them, and we know that they have continuation. And if chi is non-trivial, they do not have any poles. So, so Artin gave evidence for his conjecture. He proved this, and the statement that an LS rho equals an LS chi is non-trivial, and this is really an example of a reciprocity law. So this is Artin reciprocity, and it works not just for K over Q, but for more general extensions. And the statement that an Artin L function is a Dirichlet L function, or more generally a Hecke L function with Grossing character or a Del class character, is an important statement. It's the start of class field theory. Okay, so so that's stuff coming from arithmetic. And by the way, it's an interesting question as to how you get these rows, and that leads us into the domain of arithmetic algebraic geometry, and you might think about something like a Shimura variety, where a Galois group acts on some cohomology space. And so there's an interesting question as to how you get the LS rows as well, which is also part of the Langlands program, but maybe not the part that I'll spend too much time talking about today. Okay, so that's a collection of arithmetic L functions. So LS rho sort of are L functions coming from arithmetic, and arithmetic gives L functions. And the LS chi is a different kind of object, and this is something which gets generalized to say that automorphic forms, in the sense of Harish-Chandra, also give L functions. And to explain that in any detail is a long story and quite a beautiful and involved story. But for now, I don't want to explain that story in any detail. But what I want to say is that according to Artin, we should be looking at objects that are entire. And in fact, this theory of automorphic forms gives rise to not merely L functions, but L functions that are entire. So in fact, if I is an automorphic representation on L2 of GA mod GF, which is cuspidal, and maybe I'll just start by doing GLN, and I maybe want to even mod out by the center. I could put in a central character as well. So let me not do the general case just yet. Let me start with the first case. Okay, so let's start with GLN, and this is the space that Harish-Chandra was giving us, and so just to say a little bit more about this before I can finish the sentence. So in Harish-Chandra's work, we were looking at a real Lie group, but we might go from the real points to the adelic points by a strong approximation process. And so this is the group, and we had a gamma in Harish-Chandra. He had the gamma on the right. I'm going to put it on the left, but this is the discrete group, and he had semi-simple, so I'm modding out by the center. Okay, so this is a space of L2 functions on a group modulo a discrete group, and it's a generalization of the space that Harish-Chandra was looking at. and we had a growth condition, if you remember, that we had an F0, and so this cuspidal is some kind of a growth condition. So if pi is an automorphic representation, say on GLN, a generalization of a classical modular form, then there is an L function, Ls pi, and for the experts, this is the standard L function I have in mind. And it's a theorem from the theory of automorphic forms that, like the object, I guess I should have said it, this only really makes sense if the real part of S is sufficiently large. And in fact, Artin proved that its real part of S greater than 1. And then so this statement about it being entire implicitly assumes that it's not merely defined for real part of S greater than 0, but it has a continuation, and the continuation is known to be meromorphic. So the issue is whether or not it's entire. So in our case as well, there's a similar function. It's defined. It's initially defined for real part of S in a right half plane, but it has analytic continuation to all complex S, and I do mean analytic for the case of cusp forms in the standard representation. And just like the Riemann zeta function and just like the Artin L functions, it also has a functional equation under, say, S goes to a reflection of, and I'll just make the reflection at 1 in the sort of standard way we're all used to, so that the center of symmetry is the line real part of S equals a half. Okay, so what I want to emphasize is that there are two different ways of getting L functions. One is from arithmetic, and another is from analysis, from L2 functions, from harmonic analysis on a natural space attached to a group, and it's a space exactly which Harish-Chandra studied, was one of the very first to study. Okay, and then by a process which takes some work to explain, there is a way of taking the analytic objects and getting things that are very, very nicely behaved. They're Euler products, they're defined in a right half plane, but they also have continuation and functional equation. And Langlands' first idea is that the reason that Artin's conjecture ought to be true is that every Artin L function is an automorphic L function. It's one of those objects that I described that come out of harmonic analysis and then doing something to those functions in a very systematic way that gets studied over many years by a big group of researchers. And because of that, Artin's conjecture is true, and it's true for a very specific reason, that there's a connection between things coming from arithmetic and things coming from harmonic analysis. Okay, and you might properly think of this as a conjecture about generalized reciprocity laws. And so it's an amazing insight, and it's an explanation for why Artin's conjecture ought to be true. Now, the optimist might say, great, now we understand these are just two versions of the same thing. There are objects coming from arithmetic, there are objects coming from analysis, and they're the same objects, but that's actually not true. So most functions in this L2 space, say for GLN F, the center of A, most of those functions are, in fact, not coming from arithmetic. And in fact, Langlands calls them transcendental, and I think that his description of that word should be taken very seriously. And so in the beginning of this talk, I recalled Harish-Chandra's theorem about a multiplicity being finite dimensional, and asked, and pointed out that even in simple cases, where we expect it to be one-dimensional, and there are computer experiments that say it is, we don't actually know how to prove it. And you might then ask, what's the difficulty? Well, in some sense, the difficulty is we're trying to describe transcendental objects, objects that we really should think of as transcendental. And so it's very hard to get your hands on transcendental objects. And many years ago, when I was a student, Dennis Hedgel told me he believed that every eigenvalue lambda itself should be transcendental, and that if you normalize the Fourier coefficients, you can maybe choose one of them for free because you can multiply by a constant. But if you make one of them, say 1, then the other non-zero Fourier coefficients should all be transcendental. And I guess probably for most of these, they should generally be non-zero. But these are all very, very hard questions because we're working with things that come from analysis. And but when they don't come from arithmetic, they're much harder to understand. And I'd say that we really don't have the deep understanding of them that we would like to. So this is already a wonderful insight of Langlands and incredibly important. But what's very dramatic is that Langlands takes this connection and goes farther with it. Okay, so Langlands makes the following conjecture. Has the following viewpoint. There are lots of things that we know how to do on the arithmetic side. And that's a bit vague, but let me try to be more precise. These are things that we can do basically coming from linear algebra, multilinear algebra. And I'll give some examples of these because they really cut to the heart of the theory, that there are lots of things that are very easy to do when we have something coming from a Galois representation. And Langlands says that even these things that are easy to do in the world of arithmetic should also be things we can do in this transcendental world for all automorphic forms. So Langlands proposes that, Langlands conjectures that these have extensions or generalizations or matching for all, say, nice cuspidal automorphic forms. And cuspidal isn't absolutely necessary, but there's maybe slightly more to be said. Okay, so that when we can do something in algebra, there should be a version of it that works for this L2 space that Harish-Chandra was describing. And so I want to give some examples of this because it's really quite a profound idea, it turns out. So first example, we imagine, remember, that our context was rho going from the Galois group, and I forget my base field, and I should get it right. It's K over Q to odd V. But lots of times I can take one matrix group and embed it in another matrix group. So let's suppose that there is a representation we'll call it sigma from ought V to some other vector space ought W, where, oops. And so this might be, say, a complex analytic homomorphism, where W is another complex vector space. Sorry, let me get this written down properly, where W is another finite dimensional complex vector space. So for example, we're used to such a thing. We have all sorts of examples coming from linear algebra. We might let W be the symmetric mth power of V, and then there's a natural representation from V to its symmetric mth power, for example, and of rather automorphisms of V to automorphisms of its symmetric nth power, just sort of in the obvious way. Okay, so in that case, so on the arithmetic side, we can start with rho from our Galois group of K over Q to aught V, and then simply put in sigma and do the composition to get a map from the Galois group to aught W. Okay, so in that case, attached to first applying rho and then applying sigma, we would get something on aught W, and then Langlands conjectures there is an automorphic form on GLW. So in other words, in the particular case of arithmetic, we might have a map from, say, automorphic forms on GLV to automorphic forms on GLW. Okay, so for the automorphic forms coming from arithmetic, for arithmetic forms, cohomological automorphic forms or something like that, I might have a map from automorphic forms on one group to automorphic forms on another group. And then Langlands says that's not just something happening for arithmetic. And so Langlands conjectures a general map, and it's described in terms of the L, it's described in terms of the L functions matching, so I'm not going to write that down in great detail, but when Min-Young Kim spoke, he talked about the Satake isomorphism, and so we would have a good way of understanding the local theory, and so it's consistent with the statement that the L functions work is consistent with a local statement, and to really formulate this properly, you need to talk about things like the local Langlands conjectures, which I think were also mentioned a couple of days ago, if he was true to the slides he sent me and had time to say that. So there's a lot of structure about exactly what this map is that maybe you already heard about before my talk. But the point I'd like to take is that we can do something very easy in the world of arithmetic, and Langlands conjectures that should also work for these transcendental objects for all L2 functions that are nicely behaved, and there should be a systematic way to do this. So I might just take a second to say, why is this hard? I mean, it was very easy on the arithmetic side. So why is it hard on the analytic side? So we have a function from going back to GR group, G mod, say G1 being the first group, I'll call that G1, okay, to C or to some finite dimensional complex vector space on which there's some representation of K acting. So this is what we have. So given this, we have to take something on one group and we have to make some big F from, say, G2, a totally different group, to C. And, there's lots of ways we can imagine doing that. We can imagine some kind of induction process. But what makes it really hard is that these functions are invariant under discrete subgroups. So remember, we had the rational points embedding discretely inside the adelic points. And so I have, one group, and then I have a totally different group. And so it turns out to be very hard to take a function little f and then make a function big F in some systematic way that respects this structure of L groups. So this turns out to be hard. So we need to construct an L2 function. And just in practice, it turns out that this is very hard. And the thing that really makes it hard is showing that your object is invariant under this discrete subgroup. And so it turns out that on the arithmetic side is straightforward, but on the analytic side, it's much harder. There are other things we can do too. So for example, if I have row 1 from my Galois group to GL V1 and row 2 from my Galois group to GL V2, then it's not too hard so I wrote ought and now I'm writing GL. Of course, it's the same thing. So it's pretty easy to take that data and make a representation on the tensor product V1 tensor V2. Okay. And these are just complex vector spaces. And so once again, it's very easy on the arithmetic side, but we then would expect a map from automorphic forms on GL V1 cross automorphic forms on GL V2 to automorphic forms on GL V1 tensor V2. And again, respecting L functions. And in only a few cases is such a map known, but we don't know how to, say, take GL4 cross GL5 to GL20. We don't know how to do that at all. That seems very, very, very hard, and yet it's so natural on the arithmetic side. Okay, and in fact, it's so hard to do that. In fact, people study things like the attached L function, which would correspond to tensor product. And we are expecting that it has all these nice properties. And so even if we don't know that there's something on a very large group that for which this is an automorphic form, we can at least study the L function and study its properties. And that goes back in this particular case for the general linear group to Rankin Selberg, who did 2 copies of GL2, and then to Jacquet, Piateski, Shapiro, and Shalaika. And when we get to other groups, it's still there's still quite a bit to be said that's very recent. So we can try to study this L function and show it has the expected properties. And this is sort of a little bit disappointing. We'd like, following Langlands, to really show that there's some automorphic form on the big group, which matches it. And so we get the properties from that observation, but we don't know how to do that. So Langlands' vision is actually leads to lots of questions that are not yet known. And good. Okay, so let me just take a quick breath and ask if there are any questions before I go on and start changing from GL to other groups. Any questions before I go on? All right. Well, let's see. So I don't want to give a full account of this theory, but I wanted to give a little hint about it because I think it's pretty important, and you'll see it leads to lots of recent questions. So we started with a representation of a Galois group, and it went into the automorphisms of a finite dimensional complex vector space. But let's imagine that actually it goes into some subgroup attached to an algebraic group contained in odd V. So for example, I can imagine that everything in the image of the Galois representation doesn't just act on V, but say it stabilizes a symplectic form. So I might let V be a symplectic group contained in odd V. And for that to make sense, I need the dimension of V to be even. And in a similar way, instead of a symplectic form, I can imagine, say, a non-degenerate symmetric quadratic form. And so I could go into an orthogonal group. And so, so we might ask, what do we do in the automorphic world when the Galois representation has a special property that it goes into a subgroup of the full general linear group of V? Okay, and then Langlands proposes that rho should be attached to an automorphic representation which comes from an L2 space, and it's not actually L2 of H. That might have been what you would guess, but it's the dual group. which also again came up in Min-Young Kim's talk. So H check is the Langlands dual group. And if you remember, he described it as looking at a base root datum and swapping roots and co-roots and weights and co-weights. So it's changing, long and short roots essentially. So H check the dual group. So here, for example, if H is SP V and the dimension of V is N, which again is even, then the dual group would be SO 2N plus 1C. So that turns out to be the right group in this case. And so we would say that the Galois representation not only has sort of a version, it comes from an automorphic form on GLN, but it also comes from an automorphic form or representation on SO 2N plus 1. And for the experts, if the group isn't a split reductive group, then there's more to be said. And I think actually even Min-Young hinted at that, and we'd like to put in the Galois group more systematically so that we weave this together with the original conjecture of Langlands that I spoke about. And there's some stuff I'm not going to do, some of which I think Min-Young already hinted at, but I think I can give you the flavor of what's going on here just by sticking to this situation. So I'm going to do that right now. Okay, so once again, in arithmetic, we can imagine there's a situation, and then we're going to try to generalize to all automorphic forms. And but I do want to point out this L2 space is again an L2 space of the sort that Harish-Chandra was talking about. He wasn't just thinking about the PGL or something. He was thinking about a very general group and studying spaces of L2 automorphic forms. And so it's not surprising that once again, that work plays an important role. And again, I think it's an indication of the influence of the ideas of that he brought forward, and also Langlands and Gelfand and others at that time, Godemont, brought forward, which have played such a great role today. Selberg, for sure. Okay, now, so let's just think about that a little bit more. So, so I'm just going to take row as above, meaning on the page in front of you on your screen. So it's a Galois representation, and it happens to land inside a symplectic group that sits inside of a general linear group. Okay. And in fact, if you look at what I've told you, there are two automorphic representations attached to rho. We just got through saying that there should be an automorphic representation on SO2N plus 1 attached to rho. And also, there should be an automorphic representation. And here, because it's easier to keep track of the dimensions if I write them in instead of writing odd V. Let's see. Oh, I'm sorry. N is even. So I should have made that 2N. Sorry, that was a typo. Dim V is 2N, and then H dual is SO2N plus 1. I apologize. Okay, so keeping track of that, we're in a world of even dimension. We have two different automorphic representations. One, because we can just forget about rho going into H, or we can remember that rho goes into H. And so we actually have two different automorphic objects attached to the same piece of arithmetic information. And so Langlands conjectures that there should be a general map from automorphic representations on SO2N plus 1 to automorphic representations on GL2N. And in the world of L groups, in the world of L functions, it's the easiest thing. The L functions just should match, maybe in almost all places, but the L functions are basically the same Okay, so we're not sort of learning much from Artin's conjecture about this, but on the other hand, if we're interested in these spaces of L2 functions, again, going back to Harish-Chandra, then it's really pretty striking that there should be automorphic forms on two different groups that are intrinsically connected. And so this is really, really very, very striking. And when you think about my my comment that what's hard about an automorphic form is that it's invariant under a discrete subgroup, here I'm looking at functions on one Lie group that are invariant on one discrete subgroup and functions on another one, or on the adelic points of an algebraic group, if you prefer. The Lie group was going back to the language of Harish-Chandra. So in either way, we have these two different groups, and we're looking for functions that are invariant under different discrete groups. And it's really a surprising statement that, in fact, they should match. And then we can even start to imagine talking about, you know, the fibers of this map and things like that. So there's quite a bit we can start to imagine. But the conjecture already that that there is such a map is a striking conjecture. And this gets called an endoscopic lift. And endoscopic is a word actually proposed, first suggested by my colleague at Boston College, Avner Ash. And an endoscopic means it sees inside. So sitting inside of GL2N are these automorphic forms or representations that really come from this other group whose dual group is just a subgroup, whose dual group is the symplectic group, sitting inside of GL2N. And so we're seeing something in GL2N that's inside of it and comes to it from another group. And so that's the sense of endoscopic, and why we pronounce it slightly differently than they do in medicine. So this turns out to be really quite a hard question. And Arthur has developed a trace formula that addresses this. And the trace formula, you know, is quite a substantial machine. In particular, the work of Ngo on the fundamental lemma gets used. Work of Walt Verger on stabilizing the twisted trace formula. And in fact, Arthur's book has some preprints which are not haven't yet been released. So we don't quite have all the details of it, but it's a monumental work. It describes the local theory. It describes the fibers in a very systematic way, and it shows a tremendous amount about the structure of these groups, which turns out to be very intricate. And so there we are. So though maybe not every step is completely written out and released, the trace formula method does establish this. And so you might ask, is there another way to establish it? And it turns out that there is. So there's an alternate approach. And the alternate approach is about L functions. And if you remember, attached to an automorphic form, there's a big machinery that gives you L functions. In fact, it could give you collections of L functions, and there's been a great deal of work over 50 years or so to understand how to take automorphic forms and write down L functions and prove their analytic properties are what we would hope they are. And it's a remarkable fact that it has those properties. I mean, after all, these properties are like the Riemann zeta function, and we know from Hamburger's theorem that the Riemann zeta function is a very rigid object in some sense. So the idea is that if enough L functions attached to an automorphic, attached to an adelic representation, I, which is the restricted tensor product of local representations. So if enough L functions attached to an adelic representation behave well, what might I mean by that? So we might have L functions with analytic continuation, maybe except for some poles or whatever, some functional equation, entire and bounded and vertical strips, some things like that. So if enough L functions behave well, and this can be obviously needs to be sharpened considerably to be usable, but if enough L functions behave well, that can't be a coincidence. Then in fact, pi is automorphic. And in fact, we really apply this when it's cuspidal, so the L functions don't have poles; they're actually entire, and that's the situation where we really will be using such a statement. And so that's an idea that goes by the name of the converse theorem. And for GL1, it really goes back to Hecke probably, though again with going maybe antecedents going back to Hamburger, and then for GL2, it's the famous contribution of Weil, which gave credence to the Shimura-Taniyama conjecture and allowed us to see how it one had to have L functions attached to elliptic curves being modular. It really pointed us in that direction, and so so again Hecke, Weil. And then for GLN, it's the work of Cogdell and Piateschi-Shapiro that if I take pi on GLN of the Adels, then in a very precise way, there is enough information about L functions that one could seek to get. And if you were able to get that, then you would know that pi is automorphic. So I mentioned earlier that it's very hard to prove something is automorphic, and here's a way to actually do so. And this approach was used by Cogdell, Kim, Piateschi, Shapiro, and Shahidi to prove endoscopic liftings without the trace formula, but they were able to do it for certain automorphic forms, cusp forms. And the ones that they were able to handle were ones that are called generic. Generic means that they have a Whittaker model, and we know that some automorphic forms are generic, some aren't. So a holomorphic Siebel cusp form, for example, generates an automorphic representation that is not generic. So their work using the L functions method was very exciting, and it really was the very first proof of an endoscopic lifting in some generality before the work on the trace formula had come to the point that it is now. And then the other work I wanted to mention is work of Yunxin Kai, myself, David Ginsburg on one paper, and one really critical paper that got the whole project started, and then Eyal Kaplan, and then Tsai and myself and Kaplan have written several more papers working on this, and then Kaplan also has a paper with Dima Gurevich, which plays an important role. But what we can now do is we can prove endoscopic liftings for all hospital automorphic representations of classical groups. And we work actually in the split case. And we also can actually do a case that Arthur didn't do. We do we actually do a G-spin case, which was not covered by Arthur. And the key advance is to go back to those L functions for tensor products and understand the L function for tensor products of pi on one of these classical groups or G-spin, and sigma on GLK, and show very systematically that these L functions have the desired analytic properties. Okay, so show that these L functions are nice analytic continuation, functional equation, and entire and bounded and vertical strips. And we show that these L functions are nice, and then we're in a position to use the converse theorem of Jim Cogdell and Ilya Viatesky Shapiro. And for those that have heard the words, the way we prove these are nice is by a new Rankin-Selberg integral. And the Rankin-Selberg integral uses all sorts of ideas from representation theory involving generalized Spey representations, Eisenstein series, and their behavior. There's a sort of subtle unfolding process. It's a generalization of the doubling integrals that were first written down by Piatesky, Shapiro, and Rollis. And so we've been able to generalize the doubling method, and that does allow us to give an independent proof of endoscopic liftings that is separate from the trace formula proof. Okay, so I wanted to leave just a couple of minutes for questions at the end, so I think that's a good place for me to stop this talk. And I welcome questions and comments and suggestions, and thank you very much for listening.
Thank you so much, Solomon. So I invite the audience to have any comments or questions.
Please,
Manish?
just jump right in.
Oh, just jump in. Okay.
Yeah,
just
Ron,
a very, very nice overview of very difficult stuff, of course. I was just going to make a comment about the Selberg conjecture that you mentioned at the very beginning, 3/16 as opposed to 1/4. And I think the 1/4 would come out if you had this functoriality of all these symmetric powers that you alluded to in the middle of your talk. And I'm just wondering if there are some experts there with how far do we know? We know something. Ginsburg, for example, I think proved entirety of the symmetric fourth and fifth powers, right? If I'm not mistaken. And I'm just wondering whether the 3/16 is improved using some of the higher symmetric power L functions that we do know are entire.
Yeah. Yes, that has been improved, and I think there are slightly better results over Q, if I remember, than for a general number field. But there are, it's work from quite a long time ago, and I don't remember the world's record right at my fingertips. I know Bump had a paper with Hofstein and Ivanich, Duke and Ivanich, if I remember right, which had an improvement. And certainly each time one can get some kind of a lifting, then one does get an improvement, just as you said, and as I think you know very well, and you've contributed to understanding of. So there are, I don't remember the present world record, but certainly and if there are improvements in say symmetric power, our understanding of symmetric power L functions for Moss forms, then we would get better bounds at each time. That's absolutely right. Yeah, thank you for the comment. It's a good comment. And yeah, and I should also say that the Ramanujan conjecture, the finite prime analog of that also, again, is something that each time we know a bit more about Langlands functoriality, we do get information in that regard. So thank you. That's a comment I really meant to make, it should have made, and I really appreciate you bringing it forward. Thank you very much.
Thanks, yeah.
In the local version, at least, we look at irreducible objects only, and what is the if we look at reducible objects, do we have notions like this?
Yeah, I mean, implicitly, I was always talking about irreducible automorphic representations, and so that I suppressed some of those details, but you're absolutely right. And so and in fact, maybe there's a whole comment there that there is a whole local version of the story of the local Langlands conjectures, which I think Manish, you're an expert on, so that's important to say. There also are function field versions of these conjectures, and for function fields, there's nothing transcendental, and one has extra tools from geometry. So there have been a lot of interesting developments lately using those tools and helping to point us in the direction of what we ought to expect for number fields. And I think that will come into some of the discussion of the relative Langlands program that maybe will be part of this later. And we also, by the way, can look at representations on non-complex vector spaces, say, but on p-adic monic spaces. There's a p-adic Langlands program. There are other directions as well, and that are all part of the story. And so maybe another thing that, since you asked the question, it's a good chance to say that. And so I'll pass that, put that out there for everybody to be aware of as well.
It's all this lifting from classical group to GLN that you spoke about. So there is also the backward liftings. And
Absolutely.
so the story is quite complete that self-dual representations of GLN, which have a certain parity, are somehow in bijective correspondence with representations on classical groups, and one understands something about the packets and so on.
Yes, that's exactly right. So you can actually construct the entire L packet by taking the ideas of this of these Rankin-Selberg integrals and pushing them forward. And that was done by Ginsburg and Sury, and they have what they call double descent. So they have a beautiful paper on double descent, and it's quite striking. They can construct a whole L packet by means of generalizing the backwards lift. Yeah, thanks for that comment. Absolutely right. And so the whole question of these fibers is really a beautiful and interesting object of discussion. And so it's really quite striking that you can use these methods to actually construct the whole L packet.
This work is already written up and it is all complete.
Yeah, for split groups, it's complete. I really think these ideas can be pushed forward. And, there was a lot of work. I mean, in fact, the paper where we've done this is still not accepted. It's been floating around for 5 or 6 years now, and it's in its 150th version or something like that. And maybe someday, because people want to make sure it's fine. I know of no issues whatsoever with it mathematically, and it was a very long paper which we broke up into pieces and published several pieces that have appeared. And there's the last piece which is still in the editorial process after many years now, and who knows what the story is with it. But anyway, so for split groups, the story is complete, Dipendra, and for non-split groups, I think these methods really, I have every reason to believe they should work, but there's really quite a bit of work to be done to flesh that out.
And it is
so Arthur doesn't only work on split groups, and so Arthur's results are certainly more general in many ways. I mean, he does all local character relations and stuff like that, which we wouldn't get out of the converse theorem method. But I do believe that these Rankin-Selberg ideas could be pushed much further. And
I wanted to just go back to the question in the beginning that to each lambda, there is a unique function f. So is that, does it fit somehow together in any of the multiplicity one theorems that one thinks about?
I don't know how to make that fit, because I'm really imagine looking at a classical Moss form, some transcendental eigenvalue, and it's not impossible that space should be generated by two separate Hecke eigenforms, which are both Moss forms with that same eigenvalue. And because they're totally separate, they would have discrete, at finite places, we wouldn't expect them to match. They would just be matching at the Archimedean place. The Harish-Chandra modules would be the same. And so I don't know of a way to fit that in with multiplicity 1 or strong multiplicity 1 in that very direct situation of classical Moss forms. But all the numerical evidence
not a question which has been somehow studied so much in the subject.
That's right. That's right. It seems to be a hard question. And in fact, I was thinking as I was preparing this talk and having the pleasure of looking at some of Harish-Chandra's papers again, and I mentioned it to my colleague at BC, Spencer Leslie, and he said, no one's ever really formulated, or I mean, probably many years ago, but people don't somehow ask what's the dimension of this space that Harish-Chandra proved is finite. It's a very natural question, of course, but maybe because it's not so easy to address. So
of course, multiplicity 1 is closely it may be expected only for SL2Z and spherical at infinity. So there are all these cases which disallow cusp forms of higher weights, which are for SL2Z.
Yeah, I mean, I think that, since we're in the world of Moss forms, all the non-holomorphic even ones are linked by sort of the standard theory, and all the odd weight ones are linked. They're all basically correspond to the same automorphic representation. So, but I don't know of, but you certainly could look at them, and I don't know of a reason that they shouldn't be there, unless there's some, trivial thing like -1 for odd weight, so you have to go to a congruous subgroup to get rid of minus the identity or something. But you could pose these same questions. And so I'd say that our understanding of these transcendental objects, Moss forms, is very limited. And it is simply the situation. When there's arithmetic, as you know, we can do much more. And Richard Taylor and his whole school, Andrew Wiles, I mean, there's a tremendous work. But when these things are really transcendental, then our tools are somewhat limited. And I don't know how to answer that, to give a good accounting of what that dimension should be. I expect it's always 1, say in this classical case, but and again, it's not my idea. It's something that I probably was told as a grad student, I think maybe by Dennis Hedgehall, but maybe Audrey Terrace, somebody, or Harold Stark. People certainly talked about that and expected it. And yeah, but I don't think we have any idea how to answer that question. It'd be very nice if somebody could.
All right. So are there any other comments or questions? So if not, then we can thank Solomon once again. And
Thanks, everybody. Thank you very much.
Thanks all. Great talk.
And,
beautiful.
Yeah,
And
nice.
really a pleasure to see so many dear friends.
Yes, no, wonderful.
Truly a pleasure. I'm so happy to have a chance to see everybody and to
Good
connect
to
with
see
you.
Ramurthy. I am seeing him after a long time.